Welcome back to System Software. Today we're going to be continuing our discussion of compiler optimization. Recall that last time we looked at local optimization, that is optimization on a straight line piece of code without branching in or out. And we're going to continue today with global optimization on the entire control flow graph for a particular function. As before, I'm going to be using slides from Keith Schwartz at Stanford. So let's first review what we learned about local optimization last time. So as I mentioned, last time we looked at the control flow graph. The control flow graph consists of basic blocks, which are the nodes of the graph. And basic blocks are straight line pieces of code. You can think of these as machine code instructions or intermediate representation instructions that all execute as a unit. There's no different paths through that set of IR code. There's only one path through that set of IR instructions. The control flow graph is comprised of basic blocks as nodes, and the edges represent branching, possible flows of control through the program. And local optimizations are those that operate on the basic block. They can assume that there's no branching in or out, except at the first and last statements. And we saw several examples of this kind of local optimization. We saw common subexpression elimination, copy propagation, dead code elimination, arithmetic simplification, and constant folding. So to enable some of these optimizations, we looked at two program analyses that a compiler will first do in order to perform these optimizations. The first was available expressions, and this stepped through the basic block from the first statement to the last, that is, it walked forward through the basic block and tracked which variables are assigned to which expressions, so that at the end of the analysis, we knew at each program point which variables had which expressions assigned to them, so that we could then do our common subexpression elimination. The second program analysis we looked at was live variables. And in contrast to the available expressions analysis, this worked by stepping backwards through our set of instructions. And it tracks for each program point what variables are live. That is, what variables are going to be used at some point later in the program. And recall that when we stepped backwards, we started with some set of variables that we knew would be used later in the program. And whenever there was an assignment to that variable is no longer live before the assignment statement, which makes sense, right? Because if the variable has some value and then it gets reassigned and that value is never used, then the variable is not live between those two definitions. So let's take a look at our available expressions analysis. Let's just review this really quickly. So we step forward through the basic block, and we start with the empty set. So we assume that there are no assignments before this point in the code. And each time we see an assignment, we add this assignment to our set of available expressions. So now for any uses of A, for any assignments that have B being set to it, we can replace that B with A. And we continue proceeding through these statements, taking all the assignments and adding them to our set. So A equals B and C equals B is added. D equals A plus B gets added. E equals A plus B is added. And at this point, D is being reassigned. So whereas D equals AB was an available expression before this program point, because D is being reassigned, it's no longer available. And finally, we add F equals A plus B. That expression is now also available at any point in the rest of the program, at this point on. So another way to look at these analyses, a little bit more abstract way to look at these kinds of analyses, is that there's some set of values, like the set of available expressions, some set of values that exist before we encounter this statement, like A equals B plus C. And this statement somehow transforms or changes what values are available after A equals B plus C. So we can formalize this a little bit with some notation that just says the set of values that's available after the statement is equal to the set of values before the statement with some changes that are dependent on the kind of statement we're looking at. So this f is called, if you look in the Dragon book, this is called a transfer function because it takes the set of values before the statement and transfers them to a different set of values after the statement. So what these program analyses are trying to achieve, as we talked a little bit about last time, is provide some representation about what the runtime behavior of the program is going to be. So if we want to understand what the program does, as you're all familiar with, we could, of course, just test it. We can just try to construct some inputs and try to run the program. Well, why is this a limited thing to do? Well, for one, as you know from trying to debug your own code, trying to ensure that you have all possible inputs is a pretty tricky prospect to do. While you can use some cleverness to look at the conditions in your code and try to figure out how to take all possible branches, programs don't have to ever terminate, or they may have a gigantic space of possible inputs and a huge space of possible outputs. And specifying all of them may be either very difficult or impossible if the program does not terminate. So the idea behind these program analyses is to change the semantics of our programming language to give us the information we need in our analysis in such a way that we can analyze all possible inputs to the program finitely without having to worry about non-termination. So for local analyses, this isn't so much of a problem. So remember, there's no branching in or out, there's no loops, there's no conditions. So the basic block will always terminate. It's much easier to be able to run it on all possible inputs. But for a control flow graph, you may have looping behavior, you may have non-termination, and so this is what global analysis will do for us. But first, let's take a look at what it means to redefine the semantics of our programming language. So when you compiled A equals B plus C, how did you define the meaning of that? Well, you wrote a compiler that would generate a store instruction for B, generate a store instruction for C, generate loads for B and C, generate an addition instruction, and then generate a store for A. So in some sense, your compiler was defining the semantics of this statement in simple C by mapping it to machine code instructions. Well, that's useful when we want to actually have this program run on a physical machine. But if we want to understand, at least for available expressions, what the available expressions are at every point in the program, we can redefine the meaning of A equals B plus B to mean, well, after we see A equals B plus B, we know that symbolically the variable A holds whatever the value of B plus C is going to be. And well, on this slide, it may seem a little bit redundant to say that this sounds like the same semantics as what your compiler is doing, as load B, load C. But really, we are retaining the symbolic representation of this expression, not the actual runtime values of the expression. So once we redefine the semantics of our language, and all that just means is we sort of reinterpret how we process these statements. We reinterpret them. We reinterpret the meaning of the statement, and then we, in a sense, run the program under these new semantics. So we can think of this program analysis as being a kind of interpreter for the language, where the meaning of this statement is slightly different. The operation of this statement is different. Instead of trying to compute the actual value of A for one particular input, we're computing, in this case, what expressions are available at this program point. So you can think of program analysis and optimization as being a special kind of interpreter for our program. Okay, so in order to kind of define these analyses in general, we can create a framework. And actually, in practice, you can have this framework for doing this data flow analysis. It's analysis of how values move through the program, and we can formalize it by, or we can generalize it by having several properties of the analyses. We can set which direction we need to go in order to do the analysis. So sometimes we have to go forward through our statements. Sometimes for like available expressions, sometimes we have to go backwards, as in liveness analysis. We need to know how we update these values after processing each statement. That is, what are the new semantics that we're implementing? And what are the initial values? So we can formalize this for a single basic block with D as the direction, V is the set of all possible values that a program can have at any point. F is the family of transfer functions. So recall that transfer functions define how the values change from before and after a statement. And some I, the initial information at the top of the block. So I is going to be some subset of these values. So returning to our available expressions, our initial value, what is our initial value for our interpretation of this program for available expressions? Well, in this case, the initial value is the empty set. When we run, so to speak, A equals B, its transfer function adds the assignment A equals B to our set. So remember that this is actually the symbolic statement, A equals B. And as we continue interpreting these statements in our language, we build up the list of possible values that we have at each program point. So I recall as before, the transfer function for assignment removes any prior available expressions from our set of values and adds the new value to our set of values, and so on. So recall that this is as if you are running the program, but instead of running it for a particular input and computing the values according to the definition of simple C, we instead compute the values used for our program analysis. So in this case, the set of available expressions at each program point. So available expressions is a forward analysis. Its domain is the set of expressions assigned to variables. Its transfer function removes any value from the set, from V in, from the set of values into the statement, and adds the new expression available to the set of output values, and its initial value is the set of empty expressions. So let's look at liveness analysis. How do we frame liveness analysis as in this data flow framework? So its initial values is whatever variables are live at the end of this basic block. So we can, so assuming here that there's some return statement or some print statement or something that is using the variables after this basic block, that's how we initialize the set of output values for our basic block. And we'll see once we get to control flow graphs, we'll see where this initial value comes from for a particular basic block. But for now, let's just assume that B and D, we know they're used at some point later in the program. So those are our initial values for our liveness analysis. And we step backwards through these basic blocks. And the transfer function, that is the way we interpret these statements, is different from available expressions. So recall that instead of adding the expression, like we did in available expressions, we added the variables that are on the right-hand side of our assignments. Because we know that at this program point, E must be live between its definition and its use. In contrast, if D is being reassigned, then we can remove it from the set of live variables, because whatever definition was being used before is going to be overwritten by this assignment of D. But now that we've got another usage of D from this assignment, E equals D, D is live again before this program point. And because E was live, it was used down here, and now it's being assigned, we can remove it from our list of live variables because it's being assigned here. And we continue our live variable analysis as we did before, removing D because it's being assigned. A and B are already part of our live variable set, so nothing changes. And finally, we get the result that B is the only live variable coming in to this basic block. So this is review from last time, but framing this in our Dataflow framework, this is a backwards analysis. Its domain is the set of variables, and its transfer function, as we just described. If we see an assignment, we remove A from the set of values and add the right-hand side variables to the set of values. And the initial value depends on the rest of the program. So to run these analyses, we can generalize how these analyses are run. So given some analysis, knowing its direction, we initially set the out of the entry to our basic block. So this is just before the first statement in our basic block. We set that to our initial value. And then for each statement in order, whether that's forward or backwards, here we're assuming that we're going forwards, but it's analogous for the reverse case, the backwards case. We set the input values for our statement to be the output values of whatever the previous statement was. So if entry was the first statement, the initial value is set to the input values for our first statement. Then we set the output values for some statement S to be the input values processed by our transfer function for that statement. So this is just a kind of slightly more formal way of describing intuitively the steps of the analyses that we looked at in examples. Okay, so let's look at global optimizations. So recall that a global optimization, in contrast to the local optimization, works across the entire control flow graph. The control flow graph represents the flow of control for an entire function in our language. Now, it's much more powerful than a local analysis, as you can imagine, but it's also more complicated for some very subtle reasons. So why would this be the case? Well, it's more powerful because local analysis didn't handle branching of any kind. So if there's an if statement or a while loop, this local analysis doesn't really help us. But this also makes it more complicated because there are many paths of control through our program, and there may be join points where there are many preceding mutually exclusive paths into a basic block. Our analysis becomes a bit more complicated. So many of the optimizations that we saw with local analysis still apply globally. But there are some optimizations that we can add to this list. So for instance, code motion. If you remember from last time, if we have a while loop where some expression is being computed in the body of the while loop, but that expression uses variables not changing in the while loop, there's no reason for us to recompute that expression every time we iterate the loop. We can move that outside the loop. And with global analyses, we can do this kind of code motion automatically in the compiler. And so we'll look at global analysis and look at just a couple of analyses. We'll look at dead code, elimination, and constant propagation. And I'll point you to further slides if you're interested in more of these analyses. Okay, recall that dead code elimination removed superfluous assignments from our code. And in order to do that, we needed to know which variables were live on the exit after the last statement in our basic block. So how can we modify our liveness analysis to work on a control flow graph? So let's take this control flow graph that has a branch here, which would correspond to an if statement in simple C or C. But there are no loops in this graph. It's a directed acyclic graph effectively. There's no while loops. A while loop, if you recall, would have a back edge in our graph. But let's just take the case where we've got no loops, just some branching. And let's see what happens when we try to run our liveness analysis. So we first assume that there's some variables that are live at the end of this control flow graph. So this may be return values, for instance. If we have return values, we know that these values need to be available at the end of our block, end of our control flow graph. So just because there's a flow of control here, doesn't really change the fact that what variables are live, just because we have a single edge in this graph. Because from this program point to the exit, there's only one possible path. So these variables must still be live at this point in our program. We update the set of live variables just like we did for local analysis. This is within a single basic block, so we just use the same liveness analysis we used before. And so recall that X and Y are being assigned here, so we know that they should be removed from our set of live variables because they're being reassigned. And we can add all of the variables on the right-hand side to our set of live variables because we know that these variables must be live at this point in our program in order to be used in this statement. Okay, so now let's just pick a path to take in this analysis. So if we pick this branch, or I should say this branch, there's no statements between these two blocks. So the set of live variables must be the same. There's nothing that could have changed it at this point. And then we can repeat our local live variable analysis on our individual statements. And so when we do this, we get this updated set of live variables. A is removed because it's being reassigned. There's no additional variables being added to this set. If we happen to look at our other branch, then we get a similar story. We see that we get the same set of live variables at the end of this block. We apply our live variable analysis to our basic block. There's no change to our set of live variables. And so if we continue along this path, we might just reuse this set of live variables for the output set of values for our initial block here. So that gives us A, B, C, D. If we continue computing our live variable analysis for this graph, we get A, C, D. B is removed, and A, C, and D are still live at this point in the program. So we know that from our entry point, A, C, and D must have been live, otherwise there's potentially an invalid program. Okay, so that's our live variable analysis on a control flow graph. We can conceptually think of this as trying to take all possible paths in this control flow graph and computing the live variable set. So if we do our dead code elimination, we see that X equals C plus D is, because it's not live at any point past this assignment, we can remove it. Similarly, Y is not used anywhere later in the program. So it is used at this point, but there's been an intervening assignment. So this assignment is superfluous. We can remove it. Similarly, E isn't used past this program point, so it can be removed. And looking at our optimized program, this is what we see. Now we've got an empty basic block here, and other analyses or other optimizations can just remove these two superfluous branches. Okay, and that's our dead code elimination with live variable analysis on a control flow graph that has no loops. So the challenge is that with local analysis, there's exactly one predecessor to each statement. But when we do this global analysis over a control flow graph, all the statements may have multiple predecessor statements, and that's reflected in the multiple in edges in our graph. And so a global analysis must combine the information from all of the predecessors somehow in order to do this analysis over the entire control flow graph. So recall that this is the beginning of the analysis we did before. But what happens if we had instead decided to compute the live variables along this path, where instead of going to our other branch, we instead went to our initial block? Well, the results of the live variable analysis would be a little different for this block. Recall before it was A, B, C, D because we followed this path, but now we just have B, C, D. And so if we finish computing the live variable analysis for this basic block, we get CD as our result. Then when we go back and compute this path, we've got two, well, because this is a backward analysis, we can consider this to be two predecessors for this node, even though if the flow of control is going forward, these are successor nodes. But we've got some join point here where there are the results of two paths liveness analysis that are slightly different. How do we use both of these possible paths at the same time? Well, for liveness analysis, it is actually safe to assume both are true. And this is effectively set union. So we can take the live variables from both paths and say, well, at this point, we can approximate this case by saying that all possible live variables from both branches are live at the end of this basic block. So now, this is not accounting for the fact that this branch may never be taken or other properties, but this can be an over approximation of what's actually happening at runtime. And so if we continue our live variable analysis, this is what the entry to our program will be. So it turns out that you may need to, especially when there are loops, you may need to recompute the information for a basic block. So even though we had computed the live variables for this basic block, we had to recompute it when we had updated information from one of its successors. So because we have to repeatedly update basic blocks, we need a way to know when to stop. We need to make sure that we're not infinitely trying to recompute the live variables. Because as you can imagine, if a program is non-terminating or it has a huge space of inputs, you may be computing this data flow analysis for a long time, possibly infinitely. So, but for the case where there's no loops, there's a finite number of paths. Once we add loops, now we've got a problem. It's no longer an acyclic graph. It's a directed graph that can have cycles. So if we were to try to compute every possible path through this program, so a path might be top x equals 1 if statement, top x equals 0 if top. That might be one path. And the number of paths through this graph is infinite because of this infinite cycle. Now, of course, at runtime, the number of paths depends on whether this condition ever becomes false or not, whether this loop stops being taken and there's some exit branch. But just looking at our control flow graph, we don't have enough information to know whether that's the case. So we need some way to process this in a finite amount of time, so our compiler will actually finish, but compute the information that we need in a sound, in a sound or correct way, so that we actually reflect what's going on at runtime. So the way we do this is with a sound approximation. So recall that soundness says that if it's true in our model, true in if our set of live variables in our data flow analysis, if that's true in our analysis, then it must be true at runtime. But the converse is not necessarily true. If some variable may actually not be live, something may be true at runtime, that may actually not be true in our model. So we'll see a little bit later more about how to actually make this sound. Okay, let's look at an example where we've got control flow graph that now has this loop, has this back edge. And let's redo our live variable analysis in the case where we've got cycles in our control flow graph. So just as before, we have our initial value here. And for a kind of minor technical reason, because we may process these graphs in different orders, we need to have some initial value for each of these basic blocks. We'll see where that comes into play when we do this analysis, but it's kind of a sort of a technicality. Okay, so we can technically process these blocks in any order, but let's start in this gray block. And its set of output values is just the input values from the exit block. We do our live variable analysis now and find that A is removed from our set of live variables, but it gets added because it's on the right-hand side, and we add B and C. So same live variable analysis we've been doing for a single basic block. Now, just like before, we have two possible in edges to this block. So we just pick one as we did before. A, B, and C is the set of output values, which is taken from the set of input values from its successor block. We compute the live variable analysis for this basic block. A gets removed because it's assigned. And just moving kind of arbitrarily, we pick some next basic block to look at. If we look at the first basic block, its output set of values is the input of its successor. Now notice here, there are two successor blocks here. So as we did before, we union these two sets. So this is why we have this initial value. If we initialize the value to be empty set, when we union these two things, we get B and C. So this is the reason why we need this initial value in each block. Okay, so now we have reached the top of our initial block here. But we've got this back edge. We've got another in edge to this block. So let's finish processing all the blocks at least once. And just as before, the set of output values is the set of input values from its successor. And we can update the live variables. All right, so at this point, are we done? Well, not quite. Because if we were to, say, recompute the live variable analysis for this block, recall that the way the data flow analysis works is we take the input values from the successor blocks. But this has two successor blocks. It has the exit block, and it also has the block up here. And so recall what we do when we have two successor blocks. We union the set of values. And I'm arguing now, there's actually, if you look in the Dragon book, it'll prove it, but I'm arguing that this is a sound approximation to what is going to happen at runtime. So by unioning it, we find that the set of live variables at this point in the program is A, C, and D. So now that doesn't change the facts about live variables within these two blocks. But similarly, if we recompute the live variables for this basic block, we have the same situation. There are two possible successors with differing sets of live variables, so we union them to approximate approximate what will happen in all possible paths from this program point. And now that has a cascading effect on the set of live variables that enter this basic block. So we update this to show that the in set of values to this basic block is A, C, and D. So now, at this point, we would actually go through all of the basic blocks again and verify that there are no more changes to these sets of live variables. And once we know that there are no more changes, we can stop computing this data flow analysis. So just as a little summary, we need to be able to handle multiple in edges or out edges, multiple predecessors or successors for a basic block. And we need to handle the potentially infinite set of paths through the control flow graph. And it turns out that we may need to iterate over these basic blocks multiple times in order to compute the final value. And as kind of a technical value, we need some reasonable default value for these basic blocks to account for what its property may be, or what the live variables may be before we have processed that block, because there may be multiple successors and we haven't computed this basic block yet. So we need some value to represent, okay, we have not computed this live variables yet. So this is kind of, you can look in the Dragon book, this is kind of a more formal treatment of this global variable analysis. You have some initial value for your sets of input values. You've got your initial value for the entire analysis. And then you repeat this algorithm until no changes occur. So for each statement, or you might say each basic block of this form, set the output to be the union of the input values for each successor block. So that was here. We did the union of the successor blocks. And then do our update, do our live variable update. So we set the input for that statement to be the output minus any variables that get killed, plus the variables, or unioned with the variables that get used. So this is what's called fixed point iteration. You repeat this entire process until you notice that no more changes have occurred. So we need to show that this program, there's a couple things we want to prove about this. We need to show that it's sound, that it actually reflects what is happening at runtime, so that if we make any changes to the program, any optimizations according to this analysis, that the program will still compute the same thing at runtime, for whatever we mean by the same thing. Same inputs, get the same outputs. But we also want to guarantee that this algorithm will actually stop running. We have these infinite in the graph without any additional information. There's a cycle, so there's a potentially infinite set of paths that we take, but we want to show that this will terminate. So for liveness, the argument, and you can look in the Dragon book for something more formal, but the argument for termination is that there's only a finite number of variables and only a finite number of places where the variable can be live. So, and once a variable is discovered, it's just going to stay live for the rest of our analysis. And so because there's a finite number of variables, there's only a finite number of things we can add to these sets. They're never removed from the sets. So the program, you'll always reach a point where there are no more changes to our sets because they're finite. Another way to look at this is that you can just assume that all variables are live all the time in the program, and so our data flow analysis won't go farther than just showing, okay, all variables are live at any point in the program. The soundness is that when we compute the union of these sets, the variable will only be in that set if it was actually live on some path leaving that statement. And so similarly, another kind of intuitive way to look at this is that if we assume all variables are live at all points, the resulting program, assuming that that will also hold, that won't change anything at runtime if we do, say, our dead code elimination. Anyway, so you can look in the Dragon book for more like formal discussions of those, soundness and termination. So in order to reason about how we compute these values, these data flow values, these values in our new semantics for the language. So instead of computing the actual values of variables, the values in our data flow analysis were sets of live variables. There's a formalism that we can use in order to represent these kinds of combinations of values from multiple paths. And this formalism is called a semilattice. And a semilattice is a way, is a tool from math that describes orderings of values. So you're all used to the classic number line, where you've got, and this is called a total order, where for any two pairs of values in our set of numbers, one is always greater than the other. So with a semilattice can reflect a partial ordering. So a partial ordering is just like a number line, but instead of for any pair always having some pair that's greater or less than the other, some value being greater or less than the other, with a partial order, some values may be neither greater nor less than each other. So just to give some of the formal language here, there's always a unique top element, which is, kind of like the maximum, you might say. And there's always some meat, that is an element that is smaller than both things you're comparing, but it's the largest smaller one that you're comparing. So that you can think of as the greatest lower bound. So for our data flow analysis, the top element we're going to use to mean we have no information yet, or it's the least conservative answer. So for live variable analysis, that was the empty set. We don't know anything yet about our analysis yet. That was our top element. And so let me show this graph here. So our top element was the empty set, meaning we know no information yet. And as we merged information from paths, like if we find that one block has A live and another successor has B live, then in order to describe the case where there is a join point between these two blocks, we compute the greatest common value, the greatest common lower bound between these two values. So the lattice, it's kind of like a very complicated number line, shows us where the greatest common lower bound for these two values is, and it's given by A and B together. So for liveness analysis, the union is the meet operator. So the union says, given two values A and B, if we union them, that will give us the greatest common lower bound for those two values. So you can think of this as just a complicated way to look at a number line rather than being a line, because we have partial orders, because neither A nor B is greater than or less than each other. There is effectively a whole bunch of number lines collected together in this semilattice. So just as a little, to avoid any confusion, this is not a control flow graph. This is a representation of the ordering of elements in the values that we compute during our data flow analysis. So let's see, I think there's some examples here. So this is the top element. And there's kind of a little algorithm you can use in order to compute the meat of any two elements. You can just sort of follow the graph to their ancestor, to their greatest common ancestor. So similarly, if we've got A as our value, so A is live on one successor and B and C are live on one successor, then the greatest common lower bound is just the ancestor in this lattice. So it's A, B, and C. That's the nearest common ancestor in this graph. So anyway, these are sort of formal definitions of the meet operator. You can cover this in the Dragon book. You can call this the greatest lower bound. Every lattice has some top element, which is kind of the maximum upper bound. So just as an example, you can think of a set of natural numbers. It's kind of even though the natural numbers are a total order, you can represent it as a lattice. There's no partially ordered elements, but it's sort of a degenerate lattice. Lattice is a kind of more general than a total order. But so you can go over lattices a little bit more in the Dragon book and some more formalisms around it. So for liveness, as we said before, the meet or the greatest lower bound for live variables is the union. And so this is just the proving that the properties of the meet hold for union. So for program analysis, as we said before, this if we can define this lattice, it provides a really nice solution to these problems when we do global analysis. It gives us a formal way to describe how we combine these data flow facts, these abstract values that we assign to basic blocks and to statements. And so if we want to combine them, we use the meet. If we want to give a value to basic blocks we haven't computed yet, we use the top. But this still doesn't get us to how do we make sure that the algorithm terminates and how does it sound? But we'll talk about that in a second. Okay, so we can extend this framework that we talked about before, where we've got a direction for the analysis, forward or backwards, a set of values, a transfer functions, and an initial value. And for global analysis, we can add the meet operator over these values. So these set of values and the meet operator form this semilattice formalism. And these are all the properties we need in order to define our global analysis. Now, this is one framework for doing data flow analysis. It won't necessarily be every kind of analysis, but it's quite general. There are a lot of optimizations that can be framed using this data flow analysis. Okay, so for running it, it's basically what we saw before for live variable analysis, except in general, we can say that the values are updated using this meet. So before we just use union. If we want to kind of generalize this, other analyses won't use union. They may use intersection. They may use other lattices. But we have the same algorithm. We just repeat these updates to the input and output values for our statements until no more changes happen. So this is the data flow. This is the data flow framework. You can read about it more formally in the Dragon book. And basically, as long as your lattice has a finite height, you can actually prove that the analysis will terminate. Intuitively, so just to go over this intuition, I don't think we'll go into this in more detail, but intuitively, because there is some finite lower bound here, no matter how, and because the meet operator always lowers the values, union will always eventually be the union of all possible variables. As long as this has a finite height, you can be sure that your data flow analysis, and as long as it has a finite height and you're using the meet operator, you can be sure that your data flow analysis will eventually terminate. Because the worst case that could happen is all of your statements are just the lower bound for your lattice, the bottom of the lattice. If it's infinitely high, your analysis may not terminate because every time you do iterate over all the blocks, you may continue lowering the values. Doesn't necessarily mean it will always it won't terminate, but if you have a lattice that's finite height, you can be pretty sure that it's going to terminate. Okay, so I think, okay. So the next analysis we can look at is constant propagation, and we can use our data flow framework to perform this constant propagation. So constant propagation is a super useful tool. As you can imagine, if X is only being set to one value for your whole program, which is of course, good programming practice, you shouldn't sort of litter your code with magic values. It's best to give them a name and then use them where needed. But for the kind of simplistic implementation I recommended for simple C, if X never changed, every time we use X, we would still be loading and storing it. We'd still have to load and store it from memory every time we use it. But if our compiler can prove that X never changes, X is always 6, then we can replace usages of X with 6. And as you can imagine, this would drastically improve the performance of your compiled program. Okay, so let's reason about this a little bit. How can we know whether X is always 6? Well, variables can either have no value ever assigned to it. It can have a single constant value assigned to it. It can have 2 constant values assigned to it, 3 constant values assigned to it along different paths or more, or be known to have some non-constant value. So of course you can design your analysis however you want, but to make a very simple lattice for this constant propagation, we can define our lattice like this, where the top element is either undefined, reflecting the fact that we don't know any possible value, and then the next layer of our lattice is all of the integers. Now, conceptually speaking, this lattice is infinitely wide, but in practice, integers are finite in hardware. So this is just a very, very wide lattice. And the bottom element here is not a constant. That's the greatest lower bound in this design of our constant propagation. So if we see that x can either be -1 or +1, then we can, and we see that along two paths coming into a block, then we can just safely assume that x is not a constant and just say, don't replace this with a constant. We've found that x is not a constant according to this definition of a lattice. You could, of course, keep track of multiple constant values somehow if you like. But yeah, so this lattice, even though it's conceptually infinitely wide, although that's not really true in actual hardware, if we're using the machine representation of an integer, does have a finite lower bound. Okay, so let's just look at an example of this. Here's our program again. So this is a forward analysis. So we're going to start from the top, and now the output is going to be initialized to our top element, our undefined element. This is just the reverse of a backwards analysis, what we did for live variable analysis, where we initialized the input values to our top element. But now our top element is the at the output of each basic block. Okay, so when we first process this first block, the input value is the output value of the start block, and when we use the transfer function for this statement, we find that x is assigned to some constant. So if we're just keeping track of x in this example, in practice, you would keep track of all the variables. But if we're just keeping track of x, we know at this point that x is a constant and its constant value is equal to 6. Processing this next node here, we just do our global data flow analysis. The output of the previous block is the input of this block. And so there are no changes to x in this block. So x can still be assumed to be a constant value 6. We continue to perform the data flow analysis algorithm. So x equals 6 is part of the in edge to this. X is not changed, so x still stays constant 6. Similarly, if we process this block, there are two in edges to this block. One is the undefined element, the top element. One is 6. So the meat of 6 and undefined is still 6 according to our lattice. So the meat of 6 and undefined is still 6. And you're probably thinking, well, okay, what about this back edge? We'll see that in a second. So we see here that there are no changes to x at this point. So x still remains 6. We flow the value of x, the constant value of x, into this block. X is still 6. But okay, we've got a new assignment of x to a different constant. And this constant is 4. So remember our data flow algorithm. We have to continue to update every block until there are no changes. So we also have this block here. So, same thing happens here. We just flow the value of 6 through it. There's no changes to x. But the point is, the first time we iterated through all of the blocks, they all had changes. So we have to go through and reiterate through all of the blocks. And when we get to this point, when we recompute its input values, we have to use both in edges. But notice now that the out values for this block is 4 and the out value for this block is 6. So we use our handy dandy semilattice and compute the meat of 4 and 6. The meat of 4 and 6 is not a constant. So we now know at this point that x is not a constant. And this, this reflects the reality of runtime, because while x is 6 coming into here, depending on the looping behavior of this program, x may be 4 at some point in this block. So our data flow analysis, without knowing the actual runtime behavior, can over-approximate it and say, well, not being a constant here, when we actually use this for constant propagation, not a constant means we do nothing, which means we're sound. We're not going to actually change the meaning of the program. So we kind of, it's kind of like defaulting to doing nothing, this sound approximation. So we set this to be not a constant, and we have to continue to update each of these basic blocks. So that then tells us that after we, if you have not a constant and you don't do anything with x, it's still not a constant, and continue flowing that data flow information through our program. So at this point, even though it was not a constant coming in, because x is assigned, it's definitely going to be 4 here. And then, there's nothing else to change here. Nothing else changes, except perhaps the end block knows that x is 4. Okay, so then we can do our constant propagation operation now that we've computed all of our data flow facts here. So anytime the rule is very simple. If we see x being used and we know that it's a constant because of our constant our program analysis for checking for constant values, we can just replace that usage of x with its constant. So similarly, we're here, 6 is constant there. Now here, because we've computed that x may not be a constant at this point, it could be 2 different values, we say not a constant and we don't do the replacement. And here, x is 4 as going out of this block, but coming into it, we don't know whether it's a constant or not. Or we say it's not a constant. It could not be, it may not be a constant. Okay, so for constant propagation, it's a forward analysis. The constant propagation analysis is a forward analysis. We defined the semilattice before. Its transfer functions are that if x is set to some constant k, then the value is k. If x is the sum of 2 things, then we can just assign it to be not a constant. And if x is not even being changed, then the values don't change. So the initial value is undefined. Okay, so let's now move on to. So you can look in the notes here, and so the slides that I just looked at were slides 15. If you want to look more in detail on lattices and other global analyses, feel free to take a look at slide 16. But now instead, I'm going to move on to register allocation. Okay. So at a glance, when we're generating code for an actual piece of hardware, our original program has a potentially infinite number of variables, but the machine we're using has a finite number of registers. Now, as I advised you before, to implement variables, we can just always give them a memory location, and whenever you need it, pull it into a register and use that value into the register. Whenever you assign it, just use whatever the value in the register is and store it back into memory. But one really important optimization is, instead of always calling out to memory in order to use and update a value from a variable, it's way faster if we can just use a register, because we have this, as you probably should know from architecture class, there's this memory hierarchy, and the performance of each of these levels in memory hierarchy differs widely. So main memory is cheap, but it's much slower than registers. Caching improves this a little bit, but using registers, which are kind of special memory locations built into the chip, are really the fastest. So here's some kind of approximations from several years ago of the performance of these. So you can see that going out to main memory is many, many orders of magnitude slower than using registers. Okay, So you can, so the programming language kind of assumes that all variables are always live in memory at any point. Registers are much faster, as we know before. So the register allocation problem is assigning variables to registers in some optimal way, or at least some much faster way than always reading out to memory. So the challenge is that registers are much more rare. They're usually going to have more variables than registers, or you may have more variables than registers. So let's just, so this is just covering the register allocation that I recommended to you, the simplest one, where you just store every value in memory and then just always do a store or load whenever you need it. And let's take a look at an example of using this very simple register allocation algorithm. So here's our stack. So we've got all of our variables as stack allocated variables. When we, as you should know from implementing project 3 or project 2, I think it was, in order to generate machine instructions for this assignment, we have to load B, load C, perform the addition in registers, and then store the value of A back to its memory location. When we generate code for D equals A, we have to load the value of A. Of course, we just stored it. And then store that value into D's memory location. And similarly, we load the value of A again, load the value of D again, and compute the addition and store the value of C. So I think some of you already kind of pointed this out. If we use this it's very, very simple to implement this in a compiler, but you have some pretty glaring inefficiencies. We've stored the value of A and then immediately loaded it again. So at the very least, we could somehow eliminate this store and load and dramatically improve the performance of just this snippet of code. Okay, so there's been a lot of work over the past couple of decades on register allocation. So intuitively, we can, well, for the sake of time, let's just look at a first algorithm for doing register allocation. So the main goal is, we want to make sure that if D is given the same register, we want to make sure that that register is also being used in the block where it's being used. So this is very related to the live variable analysis. We knew that D was live here at these 2 points. We want to make sure that D is, whatever. If we're not going to spill D back into memory, we want to make sure that D is using the same register that we used for these 2 branches. And we can do that, of course, because for normal operation, only one of these branches is taken at a time. They won't both be assigned. Of course, if you're doing some particularly security analysis, so I have some research project where we are doing a side channel attack prevention, and if you execute both of these branches, that may not be true. That both branches you may want to execute in certain cases. So anyway, okay. So recall that with live variables, a variable is live at a certain program point if its value may be used later before it's being defined again. So we can use our global liveness analysis to do this. The live range is the set of program points where that variable is live. In contrast, the live interval is the smallest subrange of IR code containing all the variables' live ranges. So this is a very, very subtle difference. So the live interval is a property of the machine code, whereas the live range is something that we can talk about on the control flow graph. So live ranges are a little more precise, but live intervals are very simple to work with. So let's take a look at an example of a program here. So if we were to do our live variable analysis, I'll just sort of run through this. Feel free to walk through this on your own, but we've looked at live variable analysis a whole bunch. So if this is the result of our live variable analysis, then the live intervals for these variables are like so. So A is only live at the into this statement at the top, but it's no longer live in the rest of the program. B is live from the beginning of the program all the way to here, and then it's no longer live. So red is not live, green is live. C, similarly, is live from the beginning of the program until here. D has a live range as shown in green. These are the live ranges. So D is live here, and then it's live again here, but it's dead through here. The live interval would be would be just joining the beginning and end of these ranges. And similarly, EF and G have these live ranges. Okay, so given these live intervals, how can we allocate registers to these? Well, maybe you can already kind of see how this information can help us allocate registers. So a kind of simple way to do this is just look, well, okay, if we've got 4 registers, we need 4 variables being used at this point, so just allocate those registers to those variables. And this is exactly what our first algorithm is going to do. Say we've got 4 free registers, R0, R1, R2, R3, and we've got 4 variables live at the same point in the program. Well, we can just allocate all 4 registers to those 4 variables. But what happens when we encounter a new variable? Well, we see that there are only 4 variables needed at this program point, so we can reuse R0. So once A is no longer live, we can return R0 to the set of live registers and reuse it once we see E. And similarly, once C is no longer live, we can return its register to the set of free registers and reuse its allocation to F. And similarly, once all these variables are no longer live, all the registers are free again, and we can use R0 for G. Okay, that's all well and dandy, but what happens when we've got a case where there are too many live variables needed at one point in the program, more than the amount of available registers? So we've used all the we've allocated all the registers for A, B, and C. So what can we do? Well, a simple thing we can do is we can just pick one variable to evict from this variable allocation and spill it to memory, which means we just do what you did by default. You just use the variable in memory, do the load and store as needed. So we can perhaps unwisely stop allocating R0 for A. Now, this may be unwise because A has a very long live range, but let's assume our algorithm, without any other information, just sort of picks a variable to evict. And we can now use that register for D. So now A is no longer going to be using R0. Okay, so R2 is now a free register. We can use it for E. And now we have another case where we run out of registers, so we can evict one variable and use it instead for F. And similarly, B is no longer being needed, it's no longer live, so we can use R1 for it, for G. Okay, so this is linear scan register allocation. It's relatively new. It's super, super efficient. But there's some imprecision here because it's using live intervals instead of ranges. So let's forget about that. So here's a little optimization to linear scan, and it uses ranges instead of intervals. So, and also if a register must be spilled, it doesn't completely stop using that register for a particular variable. So let's take a look. So there's a paper on this that you can take a look at, but let's just look intuitively how this algorithm works. So A, B, and C are being used together here. And once we encounter a case where all variables have been allocated registers, we can use the fact that A is not live at this point in the program to reuse R for D but still use A for the first part of this. So use R0 for A for the first part of the program, but use R0 for D for the rest of the program. At this point, you can think of this as kind of splitting the live intervals. And just as before, once C is no longer live, R2, we can use R2. But again, we've got to allocate something for F. So we can, again, find another live interval to split here. So we can choose B to split its interval and use that register for F. And similarly, we can do the same thing, split the interval for F and reuse that register for G. So we can get some extra performance benefits out of this because there's more sharing of registers between variables. But of course, for other uses of these variables, we'll have to do more splitting. Okay, so D is not used at this point because if we look at our live range analysis, our live variable analysis, we know that D is not used at this point. So we can reuse it for F, where you can reuse the register for F. And for the rest of the cases, because A and D are used at these points, we've run out of registers and will eventually have to do spilling of some kind. But at least we get a little bit more optimal usage of our registers rather than always spilling A. We can actually use it in a register for part of the time. Okay, so there is a kind of optimal approach based on graph coloring that I'm not going to go over, but feel free to go through the slides and look at the Dragon book. But the basic idea is you can build this interference graph, which shows which variables are being used at the same time. You can build that from the control flow graph and then use the graph coloring algorithm to assign registers optimally. But it turns out that, so I won't go over this in detail. It is a very expensive algorithm. But it also turns out that if you look at this blog post, which I've given a link to, from the creator of LLVM, it provides some good insight in graph coloring versus linear scan and the allocator that LLVM uses, which is the greedy allocator by default. And it provides some improvements upon linear scan. So I think this is an interesting article to read. It's a very short blog post. I've given you a link to it in the syllabus here. And as you can see, this is the document explaining the code generation for LLVM. And there are actually several different register allocation algorithms that you can actually, you can set LLVM to use different register allocation algorithms and see for yourself what the different algorithms would be. So the default one is this greedy algorithm, which improves upon linear scan and does some heuristic range splitting. So I encourage you to read this blog post and take a look at. You can actually take a look at the paper for linear scan algorithms. But other than that, that sums up optimization for this class. At least it's a really, really rich field. It could be a whole course on its own. And I recommend just looking over the Dragon book a little bit. Take a look at this blog post, and you'll get a better feel for this. And I will see you next time.